Welcome to G Fun Facts Online. Today we are diving deep into a subject that sounds like a glitch in the laws of physics, the concept of a metal object that simply refuses to sink. We are talking about materials that, no matter how often they are submerged, punctured, or damaged, relentlessly return to the surface. For centuries, maritime engineering was ruled by a simple arithmetic laid down by Archimedes. It was a battle between gravity pulling a ship down and the buoyant force of the water it displaced pushing it up. If the ship weighed less than the water it pushed aside, it floated. If water breached the hull and displaced the air, the ship sank. It was a binary reality. But in the last few decades, and culminating in breakthroughs researchers are finalizing right now, in 2025 and 2026, a new variable has entered this equation. That variable is the physics of superhydrophobicity. We are no longer just building watertight hulls. We are engineering surfaces at the micro and nanoscale to repel water with such extreme prejudice that we are fundamentally altering the boundary conditions of fluid dynamics. This is a revolution that takes us from the leaves of the lotus flower to the hairy abdomen of a spider, and finally, to laser-etched laboratories where unsinkable metals are becoming a reality. To understand how a heavy metal structure can refuse to sink, we first have to zoom in, way in, to the microscopic landscape of wetting. To the naked eye, water sitting on a surface looks simple. It either spreads out or it beads up. But at the molecular level, this is a violent struggle of thermodynamic forces. The fundamental metric here is the contact angle. Imagine a single droplet of water resting on a table. If the water loves the surface, it spreads out, creating a low contact angle. We call this hydrophilic. If it fears the surface, it pulls itself into a tight sphere to minimize contact, creating a high contact angle. This is hydrophobic. For over 200 years, this was described by Young's equation, which balances the tension between the solid, the liquid, and the air. But Young's equation assumes a perfectly smooth surface, and in the real world, nothing is smooth. Roughness is the secret key. When you roughen a hydrophobic surface, you don't just change its texture, you amplify its chemistry. This leads us to the most critical concept in this field, the battle between the Wenzel state and the Cassie-Baxter state. These are the two ways water interacts with a rough surface. In the Wenzel state, water penetrates every groove and pit. It wets the roughness fully. A droplet might look round, but it is pinned to the surface. It's sticky. For buoyancy, the Wenzel state is a disaster because there is no trapped air. But then, we have the Cassie-Baxter state. This is the magic state. Here, the surface roughness is so extreme and the features are so microscopic, often nanoscale pillars or hairs, that the water droplet sits on top of the peaks, suspended by surface tension. Beneath the droplet, in the valleys of the roughness, air is trapped. The water is effectively resting on a composite surface made of 5% solid and 95% air. This creates a contact angle exceeding 150 degrees. This is superhydrophobicity. In this state, the water barely touches the solid. It glides across a cushion of air with almost zero friction. For buoyancy, this trapped air is the holy grail. It creates a layer known as the plastron. The plastron is not just a passive bubble, it is a dynamic thermodynamic shield. Think of it as Archimedes 2.0. Conventional buoyancy relies on the volume of the ship itself, but with a superhydrophobic surface maintaining a stable plastron, the object behaves as if it is larger than it is. The trapped air layer displaces water, contributing significantly to the buoyant force. A dense metal object can float if it can trap enough air to lower its effective density below that of water. The air acts as an invisible life jacket, chemically bonded to the surface of the metal. But there is a catch. As you push this object deeper underwater, the hydrostatic pressure increases. This pressure tries to force water into those tiny rough grooves, collapsing the plastron and forcing the system into the sticky Wenzel state. To prevent this, engineers must calculate the Laplace pressure. The smaller the pores on the surface, the higher the pressure required to force water in. This is why simple roughness isn't enough. To create unsinkable materials for the deep ocean, we need sophisticated nanoengineering to create energy barriers so high that water simply cannot force its way into the grooves. Long before humans began etching aluminum with lasers, biology had already solved these problems. Nature provides three distinct blueprints for us. First, we have the lotus leaf. This is the most famous example. The leaf is covered in microscopic bumps, which are themselves covered in nanoscale wax crystals. This hierarchical structure ensures a stable Cassie-Baxter state. If you submerge a lotus leaf, it shines like silver. That shine is the total reflection of light off the trapped air layer, the plastron. This keeps the leaf from rotting and ensures it always floats back to the top. Then, we have something even more sophisticated, the water spider, or the diving bell spider. This creature takes the plastron and weaponizes it for survival. It spins a web underwater and fills it with air carried from the surface on its hairy abdomen. But here's the fascinating part. This bubble acts as a physical gill. As the spider breathes the oxygen inside the bubble, the oxygen level drops. This causes oxygen dissolved in the surrounding water to diffuse into the bubble, replenishing the supply. Simultaneously, carbon dioxide diffuses out. In stagnant, oxygen-rich water, the spider can stay submerged for days, surviving entirely on the physics of surface tension. The third biological master is the floating fern Salvinia molesta. Its leaves are covered in complex hairs that look like tiny egg beaters. For years, scientists were puzzled because usually, superhydrophobic surfaces are slippery, but the fern needs to be stable. The solution is called the Salvinia paradox. The very tips of these egg beater hairs are hydrophilic, meaning they love water, while the rest of the whisker is superhydrophobic. The hydrophilic tips grab the water surface, pinning the air layer in place so it cannot slip away, while the hydrophobic cage traps a massive volume of air. It is a masterpiece of fluid engineering, using a water-loving anchor to secure a water-hating shield. Inspired by these biological marvels, researchers at the University of Rochester have achieved a massive breakthrough between 2019 and 2026. The team, led by Professor Chunlei Guo, developed a technique to make ordinary metal unsinkable using femtosecond laser processing. They used extremely short, high-energy laser pulses to etch microscopic and nanoscale structures directly onto aluminum. The result was a surface so superhydrophobic it appeared pitch black, because the structures trapped light as well as air. But they didn't stop at just the surface texture. They innovated a new geometry. They created two parallel superhydrophobic surfaces facing inward, or a tube etched on the inside. This geometry protects the air pocket. Even if the structure is forced underwater, the surface tension forces keeping the water out are bolstered by the macroscopic trapped volume of air. In their 2026 update, they introduced a divider in the middle of the tube to act as a geometric lock, preventing the air bubble from floating out even if the tube was tilted vertically. The most stunning demonstration of this technology involved punching the metal full of holes. In a traditional vessel, a puncture is fatal. Water rushes in, air rushes out, and the ship sinks. But in the Rochester tubes, the superhydrophobic interior surface repels the entering water. The water forms a meniscus at the hole but refuses to spread into the tube. The air remains trapped, and the metal structure floats, even when riddled with perforations. This effectively decouples buoyancy from structural integrity. A ship hull built on these principles would not sink even if torn open, provided the internal surface area remained superhydrophobic. But buoyancy is static, and ships need to move. This brings us to another massive benefit: drag reduction. In classic fluid dynamics, we have the no-slip condition. It states that water flowing past a hull has zero velocity right at the wall. The water molecules stick to the metal, creating a boundary layer of friction. Superhydrophobic surfaces violate this dogma. Because the water is resting on a plastron of air, which has a viscosity 50 times lower than water, the liquid can slide over the surface. This creates a slip boundary. The hull is effectively coated in a thin layer of gas, allowing the ship to glide with significantly less friction. Experiments have shown drag reductions of 20 to over 50%. For the global shipping industry, which burns millions of tons of fuel, this is a trillion-dollar opportunity. However, we must address the Achilles heel of this technology: durability and stability. The Cassie-Baxter state is metastable. A violent wave could create a pressure spike that forces the water into the nanopores, wetting the surface and destroying the buoyancy. Furthermore, according to Henry's law, gas dissolves in liquid under pressure. Over time, the plastron will simply dissolve into the seawater, just like bubbles in a soda eventually disappear. And then there is mechanical fragility. Nanostructures are delicate. A barnacle scraping the hull or a collision with debris could shear off the microscopic pillars. Once the texture is smooth, the magic is gone. Researchers are working on solutions right now, such as self-healing surfaces that release hydrophobic wax to repair damage, or active air replenishment systems that bleed tiny amounts of compressed air through the hull to maintain the plastron indefinitely. They are also designing armor-plated microstructures, where fragile nanohairs are nestled inside robust ceramic grids, protecting them from abrasion. We are standing on the horizon of a future that looks like science fiction. We are looking at ocean energy harvesters that are immune to corrosion, unsinkable sensor networks that can drift for years monitoring climate change, and perhaps one day, ships that are virtually impossible to sink. The boundary between sinking and floating is no longer a hard line drawn by gravity. It is a fluid frontier negotiated by surface tension, roughness, and air. By manipulating matter at the nanoscale, we have found a way to cheat Archimedes, recruiting the air itself as a structural partner in the deep blue sea.